Philosophy, I'm pretty happy to present here a piece of work that indeed is rooted in this Aharonov-Bohm effect, which is a effect that has been checked experimentally. It was a theory put forward by Aharonov and Bohm in 1959, and then was finally proven correct in the work of a Japanese group, Tonomura et al. In 1990s, more or less. And the work and the idea was that if you have your usual space, the 3D space with a hole in it, then the multiple connectedness or connectivity of the space would have physical effects, measurable effects. And that was a very important proof and discovery. I remember to have ran into a discussion on this with the famous Sergei Novikov, and telling me that indeed there was a remarkable result, putting on firm experimental grounds the fact that physics was definitely influenced by topology. So in this philosophy, I'm going to present you this work. And the work relies on a simple model, the Gross-Pitayevsky model for Bose-Einstein condensates. And here you have the equation written in a non-dimensional form, where the usual assumption is that as x goes to infinity, vector position, then the wave function, which in mod squared represent the density of a virtual fluid, goes to 1. So is a kind of uniform density when we are far from defects. And this is, we've been talking about this equation from several points of view in the recent days during the school. So you have a wave function psi that ultimately is function of vector position x and time t, and I'll rely also on this Madelung transform that we mentioned during the school, and that maps these complex wave function into two quantities, rho, let's say a density of a virtual fluid, and u through the grad of the phase is a virtual velocity. So in this context, we can, by doing this mapping, we can rely on a hydrodynamical interpretation of this equation and what we do with this equation. Well, I heavily rely on this hydrodynamical interpretation, and in telling you a few things, but before I need some little background. And so this first information comes from helicity, classical helicity, which we heard about, is defined as u dot the curl of u on the space of omega. And under GPE, these can be reduced to a simpler form, if you like, because the vorticity is a delta function on these null lines, and so it can be expressed as the circulation gamma times this integral along the axis of the defects, if there are any. And according to a number of authors, these can be proven to be zero. Exactly zero. And one way to see this, of course, is not so, how to say, rigorous, but it helps you to understand this. One way to see this is you just substitute u as a grad chi, and then you see if it is a closed curve that is zero. So under GPE, we have that helicity is always zero, although this zero is conserved by Noether theorem. So by classical results, you can prove in distributional sense that this quantity is conserved and is zero. So we can rely on this result of Moffat 69 that, and then extended that if we have a number of nodal lines in case of classical fluid of vortices, and these are linked or knotted in an ideal fluid, then we rely on the fact that, say, take a link with possibly different circulation in more general cases, then the helicity, the classical helicity, is just given by the linking numbers. So you have this formula that is just the classical relation of the Gauss linking number and the self-linking number, so to speak, to helicity through circulations. So since we consider in the ideal situation conservation of circulations and of course conservation of topology, that provides a proof from that perspective that helicity is conserved. On the other hand, we heard from, for example, from this morning's his talk that helicity is conserved from the fluid mechanical viewpoint. Okay, so if we explicit self-linkage, we can rewrite this expression in terms of right and twist, and this is another thing that we've been through during the school. But under GPE, this quantity is 0, so what is important is to remember that the sum of the linkages is giving to you 0 in the GPE case. Now, of course, physical effects associated with knotting and linking are not known, have been studied somehow by people in the past. And in particular, if we have no twist on a vortex ring, then through the phase contour, we can see the result of twist superposition. The twist superposition gives you the phase map, so to speak, the contour plane here. You see the contour phase that goes on the other side. It means that the phase, which is, as we heard in a number of talks during the school, is a surface that is, has a boundary on this defect. This surface is kind of rotating around the line defect. And the relationship between topological aspects and physics can be traced back, as far as I know, to a beautiful fact. Talk is here to prove certain statements that are in literature. They're not deep conceptually because they are rooted, as I said, in the Aharonov-Bohm conceptual experiment, but rigorous proof and based partly on derivation of new results and partly on hydrodynamical interpretation is straightforward, if you like. Well, we have always in mind the interpretation due to Biot-Savart. This is the induction law. And if we think of a vortex ring, as I will do in my talk, a vortex ring has a flow that goes around its center line and induces a flow at the center. And this flow at the center is what we compute in terms of the velocity of the ring if we propagate with the ring. And this is the Kelvin's formula that we all know about. Now, in this case, note, in this case, when there is only this azimuthal contribution, there is no singularity at the center. But if I add a longitudinal flow on the ring, then we evidently have to have a singularity at the center. And this is the key idea I want to investigate. Evidently, if you have a topological mind, you understand immediately what is the background of this. Evidently, there must be a linkage that is conserved, and I started saying that in GPE case, the linkage is 0, the total linking is 0, so you understand that one thing is locked with the other. Well, with Simone Zucker, numerically we investigated this problem. You can work out the velocities and the information about, for example, the ratio of this longitudinal flow with the propagation velocity of the vortex ring. You can estimate things. And in numerics, we found a number of features that are quite interesting, and so I wanted to investigate things analytically. So this is the purpose of our work that is done by in collaboration with my student Matteo Foresti in Milano, and this is the result I can state. Let L1 be a vortex ring of a given circulation, say 1, a rectilinear central vortex at the center, I said, of the vortex ring, circulation 1 coexists, can coexist if and only if L1 and L2 are linked together. I on purpose use the word of Tate, interlocked. With relative phase twist, twist 1, twist 2 equal plus minus 2. So there is if and only if, and so I go through this quickly. We have our configuration here, and the topological statement. First, if L1 and L2 are linked, then we have this result. Well, easy. because we start with helicity equals 0, total linkage equals 0. The total linkage is just twice the linking number of the system plus the contribution right and twist of the two components. But the rife of each component is, of course, 0. Remember, the rife of a planar circle is 0, and the rife of an infinitely straight line is 0. So this is 0, and so we have 0 equal to this, and evidently we have this result. Linking, of course, has to be computed in this way, and is just the sum of the crossings. I put a plus here. It can be a minus, so that we have this uncertainty on plus and minus. Now, I just like to add, for the moment, is a conjecture, but we are very close to, say, prove it. We are considering the Hamiltonian and the Hermitian form of the Hamiltonian in terms of twist, and you think that twist in terms of energy goes as a square, and so you can prove that evidently twist equal 1 gives a twist equal 2 and gives the minimum energy state of this excited state. Because remember, minimum energy is when there is no twist at all. So if you change to 2 or to 0, one of the two and the other comes 2, then go to 4, twist squared, and that gives you immediately a higher energy level for the system. So we can conclude, for the moment is a conjecture, we can conclude that twist equal 1, so if one is 1, the other is 1, or something like this, -1, etc., gives you the minimum. Now this, as far as is concerned, this direction, and then we want to say something about the other directions. In other words, that it exists, this, if that is true. And this requires a little bit more of work. So the statement is, if we have this twist present, and for simplicity I will consider the vortex ring with a twist on it, twist equal 1 on it, then there exists a second, there must exist a second defect, so that is linked with the other one. Okay, so we suppose that we consider just one defect existing, and for simplicity we take twist equal 1 on that, and for me that one would be a vortex ring. So let me define these quantities. The twist, first of all. Twist is just take a unit vector normal to the curve L, being L the line, the defect line, then the twist is defined by this formula. So you have to compute these quantities in order to have the twist, and the twist is given by the rotation of the unit vector P around L. Now, we need to have a prescription for twist. So, zero twist condition. For this zero twist condition, I will refer to the parallel transport, because I'm in space. I don't want to have to do with the particular references. I want to be in a reference-free system and non-inertial and so on and so forth. And this in literature, according to the context, change in name, but is well known in some context, for example in theoretical physics, that this is due to the Fermi-Walker transport. So this is a parallel transport, as you see, of the P framing along L. And this detects presence of twist. So the unit vector P does not rotate along L if and only if it is Fermi-Walker transported along L. And for this, I need an operator, and this operator has been introduced in the 50s, and this is this. Okay, so this is the derivative according to the Fermi-Walker transport of P. It takes a general form. Here I already prescribed it for my coordinate S, arc length along L, unit tangent T, etc. And if this is the zero twist condition, then all this quantity has to be 0 for any point along L. I will use this twist condition to prescribe and to check on the effect of twist. Well, the effect of twist implies defining a twist. Now we have a curve L, and there is no thickness on this curve, because remember, it's a null line. But I will be helped in this by introducing the surface bounded by L, by our defect, and this surface has a name, is a Seifert surface, and the Seifert surface allows me to consider the push-off on the Seifert surface of L, and therefore to introduce twist. So I take U as a P. I identify P with U, being U hat, the unit vector for my ribbon on the isophase surface chi equal constant. And by that I define a phase twist, and I prescribe that the phase twist is 0 or not 0 according to my project. So here I compute these things, and I check that this quantity is different from 0. I find the conditions, I do a little bit of algebra, and I can identify this condition explicited in two terms. One term is giving me a component along a azimuthal direction around the defect that has a little m over L there. If you like, m over L can be thought of as a winding number, or winding number per unit length, and a contribution from the local curvature along the tangent direction. So I can identify these two terms by this Madelung transform. Remember, the Madelung transform consider contribution from the grad of the phase in terms of the velocity. So this contribution as a poloidal velocity field, and this as a longitudinal field. So this means that in presence of twist, then I need to have a second defect from the hydrodynamic interpretation I gave you before, and the components are coming from the prescription of twist different from 0. Well, a twist can be injected by a phase perturbation, so you do a little analysis on GPE. I want to remind you how we get to Kelvin waves in one line. I set twist equal to 0. I have my vortex ring without twist. I look for the dispersion relation for Kelvin waves. I take the fundamental state, and I consider perturbation on the fundamental state, and then evidently I have the perturbed state given by some dispersion relation that can be traced out from plugging in this psi 1 form. Lambda is the amplitude that I take it much smaller than the fundamental state, and then k is the wave number, the wave vector. R is just the vector position of my defect, and nu is just related to the group velocity. So here I have the dispersion relation that gives you the group velocity in terms of proportional to k. This is known to be the relation for Kelvin waves. I can do the same when I perturb the systems with a twist that is different from 0. I have a dispersion relation in presence of the winding number. The winding number is just basically the information of the twist along the line. But here I just have to remember that the Gross-Pitayevsky equation is known locally phase invariant, so I have to reconsider a new equation for that. I plug in the fundamental states with this winding number in it. I consider the resulting relation from the perturbed state, and the new dispersion relation is this, which gives us some information about the group velocity, because now the group velocity is not only linear in k, the wave vector, but is also linear in the winding number. In other words, the group velocity gives us some information that we can distinguish from the basic information, the Kelvin waves. All this leads me to tell you that in the paper with Matteo, well, for the first time, at least in my experience, we attempted to propose a real experiment. So we proposed an experiment to do in the lab, and on the basis of this dispersion relation and on the basis of the actual possibility to realize an injection of twist on the present defect, we hope to have the chance to show that through twist injection a new defect is generated. Thank you very much for your attention.